We're doing something a bit different today, which is I'm going to show you how I use dynamic programming to solve this video game. So this is a mini game in a game called Mobius Front, which is a new release from Zachtronics. They make a lot of good programming video games, which I recommend. This one actually is more of a tactical RPG, but anyway, it has this mini code game in it, as most of his games do. And I played this one a couple times, and I noticed that I thought you could solve it with dynamic programming. And I went ahead and did that, and that was pretty interesting, both because it's neat, I think, to find, I don't know, things out there in life that you can actually sort of use programming for. And also, it's an interesting problem in dynamic programming. It's like a pretty, anyway, there's some interesting. Actually, finding the solution is a little bit tricky, and implementing it. Okay, so first we have to understand the game, right? So it's a code game. There's 52 cards in the deck, right? And we've dealt them out into 13 piles, or 4 piles of 13 cards each. And you can play any of the cards at the bottom of one of the piles. So there's always 4 cards to play. Well, unless you run out of the whole pile, then there's less. But normally, you can play any of 4 cards. And you play them onto this stack, right? So maybe I would play this card. And now you can see I've built a stack. And the sum of the stack is 9. That's what this is telling me. Right, so I just keep doing that. And eventually I played out all of the cards. And as I do that, I get points according to some rules that I'll talk about in a bit. And so the goal of the game is to get 61 points sort of as you play out all the cards. And so what happens, so you play some cards, right? If you play a bunch of cards that are the same, you get some points. So you can see I got 8 points for playing these 3 7s. And you can also see that they are, it's keeping track of the total of all these cards, which is currently 30. And you're allowed to go up to 31. So I can't play this 3 or this 3 or this 4 because that would put me past 31. And I can play this ace because aces are 1s. And I'm actually obligated to play the ace, right? You can't, if there is a legal card to play, you have to play that card. So I play the ace, I get to 31. That actually also gives me points. And now I have to go start a new stack, right? Because there's no card that you can play on top of a 31. That's the maximum limit. Right, but if you could play a card, you have to. And if you can't play a card, then you start a new stack. Okay, so that's sort of the rules of what cards are legal to play. But of course, the more interesting question is what cards are good to play. And so for that, we need to look at the scoring. So there's a couple different ways to get points. If you start a stack with a jack, which I can do actually, so let's do that, then I get 2 points. If I have the total of the stack is 15, I get another 2 points. If I make a 31 stack, I get 2 points. I just did that with the ace. You can also get points for playing the same sort of repeats of the same card, right? So if you play a pair, you get 2. If you play a triple, you get an additional 6. And if you play the 4 of a kind, you get an additional 12. So playing 2, 3, 4, like all 4 of a card is actually worth 20 points, right? Because you get 2 points when you put the second one down, and 6 points for the third one, and 12 points for the fourth one. So that's quite a good way to get points, right? You need 61 to win, so 20 is a big fraction of that. And then the other way to get points is runs or straights. So if you play cards that, what's the best way to put it? Right, that are sort of adjacent to each other, then you can get points for that. So for example, if I play 3, 5, 4, right, the last 3 cards are 3, 5, 4. That's a run of 3 cards. Even though they're not sort of in sorted order, they still form like a contiguous block, right? It's 3, 4, 5 is a straight, or 5, 4, 3 if you want to look at it that way. And so that's worth 3 points, those 3 cards running together. And now I can play a 4, which is worth 2 points because that forms a pair. I can go on to the next stack. And maybe I can play 10, 9, 8, or Jack 10, 9, which is another sort of blank 3 straight, which gets me a few points, and I got some points for putting on a jack first. So anyway, that's sort of how the game goes. We can do jack 5, those are worth 2 points each, and maybe 8, 8. get some points. I'm up to 32 points, so this game is going, reasonably well. Let's see, what can I do here? I'm not going to try and play super optimally or anything. I just want to sort of show you how a game goes before we get into the computer version. So I probably won't win this game. That's okay. I will play random stuff. King, queen, ace, sure. Ace, ace. 5 is 31. That's 15, 25, 31. Okay, so we're done with the game. We played all the cards. You can see that I didn't quite make it to 61 points, so I lost this game. So, that's how the game is played, right? You play out all the cards, you get your points. So now let's see how the computer does. So I'll start a new shuffle, right? And it just gives me the cards in some order. Now we will, right, so I have my program here. I need to write down the cards so the computer knows what they are. So we had Jack, King, 9, 8, Queen, 6, 7, Ace, 8, Jack, 10, Queen, Ace, and 2, 7, King, 10, 7, Ace, 2, 9, 8, Jack, 6, 6, 2, and 10, 3, 2 Queens, 8, 5, 7, 4, 3, 9, 9, 10, King, and Jack, 3, 4, Ace, King, 6, 5, 4, 2, 5, 5, 4, 3. Okay, so I think we got them all. The program should let me know if I made a typo. So now we can run it with that input file that we just made. This takes, I don't know, 15 seconds or something for the computer to think it through, and it should figure out how to play this game perfectly. And you can see they have a feature in the game where it shows you how people have done in this specific, initial set of cards. So it looks like actually this one is relatively easy. Most people have actually won this one who've tried it. And one person even got 100 points, which is quite good. Although I expect our computer will do that as well. Okay, so we thought about it, and the computer thinks it can get 112 points, which I think is better than anyone did on this chart. It's a bit not totally easy, trivial to read. I guess this is 60. Anyway, so let's see how to do that, and we'll actually play it out. So we think we can get 112, and it says we should play from the first pile, the ace, and then the 2, and then the 3, and then the 4. And you can see by now it thinks we have 7 points, which is right. And then the 5, and then the 6, and then the 6. And it says we should start a new stack here, which is right. And it says we should have 22 points, which is right. And now we'll play Jack, Queen, King. Okay, and now we'll play from pile 1, and then pile 3, and then pile 3. And now we'll play 1, 4, 1, 2. Right, 37 points. And maybe we can start scrolling down a bit. And now we should play 9, and then the ace, and then the 3, and then the 2, and then the 4 from pile 3, and then the 7 and the 5. And we should have 48 points, which is right. And now we can play from the 7, and the 8, and the 6, and the 9. And now we play 3 queens. And now we play pile 2, pile 2, pile 3, pile 4, pile 4, pile 4, pile 2. Okay, see, this scored a lot of points just by getting a big straight, right? Ace, 2, 3, 4, 5, 6, 7. you can see scores a bunch of points. And now we can go pile 1, pile 1, pile 2. And now 1, 2, 4, we can play 3 kings. And then we're obligated to play this ace. And now we can play the jack, the 7, the 2, the 4, and the 3. And now the jack and the 10, and we have 112 points, sort of as promised. Right, that's how many we thought we could get, and we seem to have done quite well on the histogram. Okay, so that was that game. Right, and we could keep doing this. Right, and if I wanted to get a perfect score in the next game, I could make a new file for this input and run it and follow the directions. Okay, so let's see how this actually works. Right, what is the computer doing? And how does dynamic programming work here? So the first thing is just sort of reading in the input. Right, so we're supposed to have 4 piles of 13 cards each. So I'm declaring like a 4x13 grid. I'm doing this in C++, by the way. I considered doing it in Python, but like even in C++, this is kind of slow. So I think it would be, maybe sort of unbearably slow in Python. So in C++. So we're reading in 52 cards, right? The input format, as you saw, is that we're supposed to write down each pile on a separate line. Although actually this doesn't care so much about the lines, just the order. So for each card, figure out what value it is, right? So this is turning each card into a number from 1 to 13, right? Like ace is 1, jack is 11, queen is 12, king is 13. And then just mark down that card in the input. I guess something to note is that for each pile here, the cards are listed bottom to top, which are the sort of order that you would play them in. And in the input file, they're listed top to bottom, because I thought that would be an easier way to sort of write them down. So that's why we are flipping the order here. And we're also counting how many of each card we saw, just because you should see 4 of each of the cards from 1 to 13, right, in a valid input. So this is sort of just checking that you typed it in correctly. And now we can actually run the DP. So let me talk about that part. Right, so this is just the card functions that we talked about, right? This is, each card as a string and its corresponding number. So this takes the string and gives us back the number. This takes the number and gives us back the string. This is how many points towards the stack each card is worth, right? So every card is worth its number, like ace is 1, up to 2 through 10, except that jack, queens, and kings are all 10, right? Face cards are each worth 10. That's what this is telling us. This is telling us what cards, we have to work with. Okay, and now the complicated thing, which you can see from the long comment that I've written, is this state idea. And so that's going to represent the current, where we are in the game, basically. And so right, the idea here is that we're going to try and basically do a brute force solution to this game and try all possible moves. And so you could think of a state as just which moves we've done so far. Right, so you're going to do 52 moves in the game, which is taking cards, you're going to play all the 52 cards from various piles. And so one way to think of the state is it's just which moves you've done so far, right? That completely determines, right? If I just told you the list of moves that I played, that tells you where you are in the game, obviously, right? You'll have to intersperse sort of getting a new stack, but like the game will force you to do that at the relevant times, right? That'll tell you how many points you got, because you could just, simulate it again, like just play those cards in order and see how many points you got. So that's one way to think about the state of the game. But that doesn't work for DP, because if you think about it that way, there's about 10 to the 28 sort of possible sets of moves to play at the game. right, you could imagine represent a list of moves. Or choose what pile to take each card from. And there are a lot of lists like that. So that would be one way to do DP, right? You could write a recursive solution, which basically says, okay, given the moves I've made so far, we can compute how many points we would get if we played, a card from pile 1. And then that will take us to a new set of moves. And so we could just try, try all possible moves from each position. Right, so if we did that completely naively, that would be basically like 4 to the 52 kind of running time, right? Because there's 52 moves that we're going to make, and every one we basically have 4 options. That's a little bit high because you can't, once you run out of a pile, you can't play from it anymore. And also, sometimes you won't be able to play from a pile because it would make the stack too big, so you're forced to play from another pile. But whatever. It's way too slow, right? So we need to do something cleverer than that. We need to compress the game states. And that's the main idea of solving dynamic programming problems, is figuring out how to compress the game state. And so the idea is maybe we don't need to keep track of the entire history of the game, right? We can just remember enough information to sort of go forward from here. Right, so when you're, computing a shortest path in a graph, you don't need to know like the history of your path so far, you just need to know where you are. And that can tell you how long it'll take from there. So what is the equivalent of where you are for this game? So here's the equivalent, according to me. We need to know how many cards are left in each pile, right? That's definitely going to be important, right? Another way to think about it is what cards we've played so far. Because the cards that are left are the cards that we're going to play throughout the rest of the game. And obviously we need to know, what those cards are going to be to simulate the rest of the game. We also need to know how much is on the current stack, right? The sum of the current stack. And we need to know that for 2 reasons. One is that you get points for having the sum be 15 or 31. And so you need to know when you hit those point totals. And the other one is that you need to switch the stack when you can't play any more cards because it would make it more than 31. And you need to know when to do those switches. And you also need to know the cards in the current stack to score sets and runs. Sets are relatively easy. You just need to know, one way to think about it is if you knew the top 3 cards of the stack, you could always score a set because you could just look at how many of those, you can check if there's a pair by seeing if the top card matches the card you just played. It's a triple if the top card and the second card match, and it's a quadruple if the top 3 cards all match the card that you played. Runs are more complicated. A run can be at most 7 cards, right? That's what it says in the rules. And the reason for that, by the way, is that the sum of the numbers from 1 through 7, which is 28, is less than 31. But the sum of the numbers 1 through 8 is bigger than 31. It's 36. And so you can't fit a run of length 8, into a stack of sum of most 31. So anyway, it goes from 3 to 7. And so if we knew the top 6 cards, we could definitely figure out if our new card formed a run of 7, because we'd have to form it with the next 6 cards. Right, so the top 6 cards is enough to score runs and sets. Okay, so this is one way to compress the state space. And now we should ask ourselves, is it compressed enough to solve, that we could actually solve the game in a reasonable time here? And the answer is, well, let's see. So if we want to know how many cards are left in each pile, there's between 0 and 13 cards left in each pile, right? There's 13 cards in each pile right now at the beginning of the game, and there's 0 cards in each pile at the end of the game. And so that's 14 different options for the piles, right? 14 numbers between 0 and 13 inclusive. So that's going to contribute 14 to the 4th power of states. Okay. We also said we wanted to know how much the current stack was. And there's 32 possibilities for that. It could be empty, in which case it's 0, or it could be totally full, in which case it's 31, or anything in between. And then the top 6 cards, right, so that contributes a factor of 32 to the number of states. And then the top 6 cards, well, each card is between 1 and 13. So if we could specify the top 6 cards by just 13, right, by just writing, you know, all those cards down. And there's 13 to the 6 possibilities for that. So if you just go and type that into Wolfram Alpha, right, we want to see, like, is that too big or not? So we said 14 to the 4 times 32 times 13 to the 6. And that is about 6 times 10 to the 12. And that is a problem. Because this should really be 6 times 10 to the 12. Because the computer can do about 10 to the 9 operations per second. So 10 to the 12 operations takes about 1,000 seconds, which is like 20 minutes. So 6,000 seconds is like 2 hours. So it would take like 2 hours to solve a game, which is not great. And even worse, the way that DP works is you need to like write down the answer for every state. And if there's 6 trillion states, then you would need 6 trillion entries in your DP table, which is like 6, right? A gigabyte is 1 billion bytes of memory. So to store 1 trillion, you know, answers, you would need a terabyte of memory. And my computer does not have 6 terabytes of memory. So that is not going to work out. It's possible, you know, sometimes you can do some like smart things in DP where you don't keep around the whole table at once. Like maybe, you know, anyway, maybe you could forget some entries, some parts, or you can compute like parts of the table at a time. So it's not totally impossible, but anyway, we don't want to wait around for 2 hours either. So can we improve on this? And the answer is yes, which is there's a way to do this better. Instead of writing down each of the cards, we can write down which piles the cards came from. And that actually tells us what they were, right? If I play the 8, and I wanted to remember that, I could either say, okay, that was an 8, which is 13 possibilities, or I could say I played the card on top of pile 1. In pile 1, there's only 4 possibilities for the pile. So that's a lot better, right? 4 is less than 13. So that's what we're going to do, right? And because we're already keeping track of how many cards are left on each pile, so if I tell you that the top card of the stack came from pile 2, and you know how many cards I have left to play on pile 2, then you know which card I just played from pile 2, right? If there's 6 cards left in pile 1, and I just played a card from pile 1, it must have been the 3, right? Because that's the card that would leave 6 cards left, right? There are currently 6 cards in pile 1. I just played a card from pile 1. Which card? It must have been the 3, because that's the 7th card in pile 1. So instead of writing down which cards are in the stack, we can write down which piles they came from. And instead of 13 to the power 6, we get 4 to the power 6, which is a big improvement in our state space. And so this is about 5 billion, which is about a factor of 1,000 improvement in the state space. That's considerable. So now we want to do like 5 billion operations and have a table of size 5 billion. And that's actually reasonable, right? If we can do 1 billion operations per second, then maybe this will take 5 seconds. That turns out to be a little optimistic, but it's in the right ballpark, right? Really, it takes maybe 15 seconds to run my program. And if we want to store a big DP table, it's not out of the question that we could store a table with 5 billion entries. And in fact, right? That's like 5 gigabytes of RAM, which is, you know, a lot, but it's not crazy. And that's what we can end up doing, actually. My computer does have 5 gigabytes of RAM. And actually, I'm going to somewhat unnecessarily use 2 bytes for every entry in the table, 16 bits. You could get away with 1 byte. So if I'm being a little, anyway, we could cut the memory down in half if we wanted. Okay, so that was a lot of text and talking, but that's actually the big idea for how to solve this with dynamic programming. If you've understood this idea about how to represent the state, then you can write a program to solve this game at this point. I guess a thing that I haven't talked about yet, which I really should, is like, how do we know what's sufficient in the state? Like, why can't the state just be the top card of the deck or of the stack? And the reason is, so basically, the state needs to give you enough information about the game that you can like answer the question, how many more points could I get if I played this game out perfectly? Right? That's the question that we're going to want to ask about, given a state in the game, a position in the game, what is the best score I can get from here? And so you need enough information basically to score the next card that you play, and also to construct the next state, based on that card that you play. Right, and so that's why we needed 6 cards in the stack, is for the scoring of the next card that we play, because we need to score straights or runs. And obviously, if we keep track of this information, that's enough to compute the next state, which we'll see that later. I'll show you it's better to talk about that when I'm actually looking at the code for it. So to recap, the state is how many cards we removed from each pile, which you can also think of like as what index we're on, right? We've removed 1 card from pile 1, and also the next card play from pile 1 is the one at index 1, right? If we 0 index. Similarly, we've removed 0 cards from pile 2, and this 2 is the 0th card in pile 2. The sum is the total of the current stack, right, which would be 8 right now. This is the top 6 cards of the current stack, or just the whole stack if there's not 6 cards, which is just 8. And this is what piles the cards came from. So these two are sort of the most interesting ones. Right? This is what we sort of would like to have. This is the convenient thing to work with. And this is the thing that is smaller, right? There's like, you could think of this, there's like 13 to the 6 possibilities for what's in here, and there's only 4 to the 6 possibilities for what's in here. And so a key fact is that you can actually compute this thing based on this and this, right, in the way that we talked about. So that's why we want to keep this around. This is going to be our starting state. So we haven't removed any cards from any of the 4 piles. We have an empty stack. We have an empty stack. We have an empty stack. Okay. So there's a bunch of things we're going to be able to want to do with the state. One very important one is, are we done with the game, right? And by that, I mean, have we used up all of the cards? So this is very simple, right? Just go through how many cards, go through all the piles, and if we haven't used up the entire pile, then the game is not done. And if we have used up all the piles, then the game is done. Another question that we want to ask is, can we take a card from some pile in the next move? And so how do you check that? Well, you can take a card from a pile. The first thing is that there actually has to be a card left in that pile, right? If we've used everything up in that pile, then you can't play from it. And the other thing is that it can't make the sum more than 31, right? So the current sum plus how much that card contributes, right? The card on top of that stack contributes to the pile, has to be at most 31. And if both of those things are true, there is a card and it would make this stack less than 31, then it's a legal move. So that's simple enough. Another question we already used to answer valid move is what is the card, the next card on top of some pile. Right, so go to the pile and look up the card. Right, so it would be 5 for pile 1. And here's the first really complicated function, which is if we played the card from some pile, how many points will we get just from playing that one card? So here's where we have to sort of write down the rules of the game somehow. So here's where we're writing down the scoring rules. So, you know, we should expect this function to be complicated because it actually has to encode how the game works. So first check that this is like a valid move that we're trying to make. Figure out what card we're playing, figure out how much it's going to add to the sum, and keep track of how many points we're going to get. So if it's an empty stack and we are playing a jack, then you get 2 points. If the new stack sum is going to be 15, then you get 2 points. If the new stack sum is going to be 31, then you get 2 points, right? So these are the first 3 scoring rules. These are all easy. Sets are a little bit harder. So if we have something on the stack and it matches the current card, then we're going to get some set points. And now we want to know how many matches there are. So this is going to be how many copies of this new card, of that card there are at the top of the stack. And so just walk through the stack, you know, from top to bottom, and well, it matches the card. Count that, and then walk backwards. So if we had 1 copy of that card already, then we get 2 points for a pair. If we had 2 copies of the card already, then we're playing the third one, and we get 6 points for the triple. And if we had 3 copies of that card on top of the stack, then we're playing the fourth one, and we get 12 points for a 4 of a kind. And it's impossible to have more than that, right? Because there's only 4 copies of each card in the deck, and we know that we're playing one of them, so there can be at most 3 on top of the stack. Okay, so that's sets, and now runs, or straights, which is the most complicated, and I'm not sure I've done this in the best possible way. But my idea is that a bunch of cards are a straight if they all have to be different. This is maybe not super clear in the wording of the rules, but that's true, right? If you have like 7, 8, 8, 9, that doesn't count. It has to be 7, 8, 9, right? Or it doesn't have to be in order. It can be like 8, 7, 9. But you can't have any, you know, extra cards, duplicate cards in the middle. You can't have any like pair in the middle of your straight. So they have to be all different, and they all have to be in a row. And so the way I thought about this is if you keep track of the minimum and the maximum card, they should be close. Right? You want to see if you got all of the cards in a row, but you don't care about the order. And they're all different. And so just keep track of the like interval that they lie in, right? The min and the max. And if that interval is small enough, then you know that you've got everything in that interval, basically. Right, so 2, 3, 1 is a straight because you have the biggest number is 3 and the lowest number is 1. And it's only one number in the middle, which you must have because they're all different. And so you must have a run of length 3. So that is what we're going to do. So keep track of which values we've seen in the min and the max. Right, so initially we just have the card that we're playing. And then sort of walk backwards through the stack and see if you get a run without length. And we're going to keep track of the biggest run that we get, which is how many points we should score. Right, if your new card makes a run of length 5, it automatically also makes a run. Is this even true? Sure, kind of. It makes a run of length 4 and 3. Well, no, that's not true. See, straights, runs are complicated. But anyway, we're going to try all possible sizes of a run. And for each size, right, we're just going to get the score of the biggest one. That works, basically. Okay, so add the card sort of that far back from the top of the stack. I probably could have stored the stack from top to bottom instead of bottom to top. Would make the indexing easier. Anyway, I didn't do that. So figure out what that card is. If it's a duplicate, then we've ruined this run and like any future runs because they're all going to include this duplicate. Otherwise, mark down that we've seen that.
keep track of them in the max, and if there's no duplicates and the interval is small enough, then we formed a run of this size. So keep track of the best size. And if we find that the best run that we form with this new code is a size at most 3, then we get points for it, right? Which is just equal to the size. And you can see, right, if you look at this rule, that's what it says, right? For a run of length n, you get n points as long as it's at most length 3, right? You don't get any points for a run of length 2. If I put down 8, 7, that's not worth anything. But 8, 7, 6 is worth 3 points. Okay, so those are the run points, and those are all the tossable points, right? We've now covered the entire sort of slate of scoring. So that's how many points you get for playing one code. That was a lot of business logic, I guess, right? This is like half of the rules of the game. Okay, so that's another important question that you can ask about a state, right? Is how many points you would get for playing a certain move. Another important question is what state would we be in after we played a card from some pile? Right, these are sort of the transitions in our DP. Right, eventually we're going to want to combine this all into a recursive function where you go through the 4 possible moves, check which moves are valid, and if it is valid, then the best possible score you can get that starts with playing that card is the number of points that you get from playing that card, followed by the recursive call for the new state that you get into from playing that card. So this is the new state you get into. So make a copy of this state, check. This is not really necessary, I guess. This is the same thing as asserting that it's a valid move. Figure out which card we're going to play. Mark down that we actually played a card from that pile. Mark down that the sum increases by the value of that card. Add that card to the stack. And then we said we only wanted to keep track of the top 6 cards in the stack. So if this is a 7th card, then throw it out. Or throw out the bottom card of the stack. Right, because we only need the top 6. And also write down that we made a move on this pile. And again, if the stack is a size 7, then we can forget about the first move that we made, or the 7th most recent move that we made, and then return the new state. So the other kind of transition that we can make is clearing out a stack once it's done, right? That is, once it's so big that you can't add another card to it. So that's simpler. Start with a copy. We're not playing any cards, so we don't need to modify the number of cards we played. But just clear out the stack, right? It now has sum 0, no cards, and no moves. Okay. This is another... Actually, this function looks complicated, but it's actually not very complicated. And this is something sort of very general for dynamic programming. It's not really very specific to this game in particular, unlike most of the other functions we've been looking at. So the idea here is the way that DP works is we're going to store all the answers to our subproblems, which are just scores that we could get from different positions in the game, in a big table. And we were talking earlier about how big that table was going to be. It's going to be about 5 billion entries big, because that's how many possible states there are in the game, according to the way that we broke it down, which is big, right? So we should use an array, a big long array, to store that table. You could imagine like trying to store, like make a hash map, a dict, to look up the answer for each state. But that's not a great idea, basically because dicts are like quite slow. You need to hash the state, which is effectively what we're doing. But then like there can be collisions. It's kind of a mess. You'd rather use an array. So this is sort of our manual hash function, which is going to tell us for a given state what index in that big array we should store the answer for that state at. So what we want to do, you can think of this really as a hash function. We want to write a hash function that tells us a different state, or a different index for every different state, right? We don't want any collisions where they both try to use the same table cell. That would be a problem. And also, we want to not like be very wasteful with our table. Right? This is another problem with hash tables. we already need like 5 billion entries in the table, so we don't want too much like wasted, or really any wasted space, right? We actually want to use all the entries. So that's sort of the requirements for a hash function, right? It needs to produce, give different like slots. You could think of it as like a locker assignment or something for different states. And also, they should be dense. Right? Every slot should get a state, that's going to use that slot. And so the way that we do that is sort of thinking of the state as a big, almost this is like a big number in a base, but I'll explain what I mean, I guess, more. So we can write it out as a big tuple, which are all of the moves in different, right, that we made to produce the current stack, the sum of the current stack, and how many cards we used from each pile, right? These are the components of the state. We explicitly do not need to include the actual cards on the stack, right? That was the whole point of this discussion that we had about how you can compute the cards on the stack based on the moves that you made, is that you don't need to remember which cards are in the stack because you could just recompute it. Anyway, write down this tuple with 11 entries in it, and then convert it into a number. Right, and this is, you can think of it as sort of digits in some kind of weird mixed space number. Right, so you can think of this as like a ones digit. And then this is like a fours digit because there's 4 possibilities for this guy. And you don't want to, you need to give him his space, right? He needs 4 spaces, or 2 bits to write down his information. So you should store, I guess another way to think about it is move 0 is key mod 4, move 1 is key divided by 4 mod 4, right, which is you throw away the information for move 0 and then you get the next 2 bits. Sum is key divided by 4 to the 6 mod 32. I0 is key divided by 4 to the 6 times 32 mod 4. Right, so basically, you just allocate enough space for each of these different integers depending on how big they can be. Actually, they're all 4 possibilities except for sum, which is 32 possibilities. And then that compresses them optimally. I guess all these sizes have any powers of 2, which is nice because we can think about bits. So another way to think about it is that you use 2 bits for each of these guys. That's 12 bits because there's 4 possibilities each, so that takes 2 bits. And then 32 takes 5 bits. And then each of these guys takes another 2 bits. So we have 10 things that take 2 bits each, so that's 20 bits. And then this thing takes 5 bits, so it's 25 total bits for the whole state. Oh, except this is totally wrong, because these aren't 2 bits each. These are numbers between 0 and 13, so these are more like 4 bits each. Actually, we're being a little bit better than that, right? 4 bits would be a bit wasteful, because 4 bits can store 16 different numbers, and we only need to store 14 different numbers. So now I need to abandon the bits idea. This is actually not 15. But anyway, you store it, I don't know, in like the next space mod 14, I guess. So this is generally a good way to convert a DP state to an index, right? Is you write down the DP state, it's like a tuple, and then you keep the final number by doing this kind of thing, right? By, I don't know, interpreting them as digits and saving space according to how many possibilities there are for each element. So anyway, that's what we're doing here. I like to think about it kind of as almost like a base conversion, right? Like this is like the 1's digit, and this is like the 4's digit, and this is like the 4 to the 6th digit, and this is like the 4 to the 6 times 32 digit, and this is the 4 to the 6 times 32 times 14 digit. Normally we think of the digits as being like equally spaced out, right? There's like a multiple of 10 between them, but you can do the math just as well if they're not all. There's different number of possibilities for each thing. So this is sort of like what place we're at. Anyway, I don't know. I feel like I'm not explaining this super clearly, but that was 2 different ways to think about it, so hopefully one of them made sense to you. Right, so we're actually going to do the conversion to an integer in exactly the way that I described. So this is what place we're at, you can think about it. Right, so the digit times the place value of the digit, digit times place value, digit times place value, and then the place value, steps by 4, steps by 32, steps by 14. I guess there's one little weirdness, which is that moves might not actually have 6 elements, but that's fine. We just put zeros at the end, basically, if it's too small. Right, that's sort of what this is doing. Okay, so that's how you get your index in the DP table. So those are actually all of the, one more thing to do with states. Maybe I won't really explain this. This is just to sort of print out a state for debugging. This is not actually used in the final program, but it was useful to write it. Bugs. So this prints out sort of the deal and how far you are in each one, and also the current stack and the sum of the current stack. Okay. So now we can actually get to writing the DP function. So DP is going to take a state, and it's going to tell us how many points we can get from the rest of the game if we played it perfectly. And so the thing that we're most interested in is how many points we can get from the initial state of the game by playing perfectly. Right? If we played perfectly, how many points do we get in the game? And we're going to use this DP table, which is, as we talked about 5 billion elements long. So we want to be a little bit thoughtful about what we're actually storing in the DP table. And I'm going to store a 16-bit number in each spot. Right? Instead of, we could use a 64-bit number, but that would take up more space. Right? Use a lot more. Memory usage is like a serious concern, basically, is all I'm trying to say. So you can see that we define score as a 16-bit number here. I think it's actually fine to define it as an 8-bit number. Because, how many points can you really get in this game? 8 bits can store up to 256. You probably can't get 256 points. It looks, as far as I can tell, you can get like a little over 100 in most games. But anyway, 16 bits, definitely safe, right? That stores numbers up to like, 16,000 or something. Or 65,000. Okay, so how do you actually evaluate a state? If you were done with the game, right, you played every card, then you get 0 points, right? There's no way to score points once you're done with the game, right? This is not, that's how the rules work. You're not going to magic your way out of that. So figure out which index in the DP table you should use. If there's already something there, then just return it. Otherwise, we should consider all 4 possible moves, right? Which is just playing a card from each of the piles. So if that move is legal, figure out how many points it scores, and also what the next state would be. And so the total number of points, if we play from that pile, is like the immediate points plus the points from the rest of the game, which is this. And so if that's better than the best move we've seen so far, then mark that down as the best score we could get. If there were no legal moves, right? This starts out as -1, so any valid move is going to score better than -1 points. But even if you play very badly, you can get at most, you're going to get 0 points or more. So if none of the 4 moves were legal, then we have to start a new stack. And you don't score any points for that, so the number of points that you get is just number of points you get by playing out that new game state. and write down the best possible points that you got and return that. Okay, so that's actually the entire DP function. It looks kind of short because we put all the rules of the game inside functions of this state class. Right, so here the code reads fairly abstractly. Right, for each possible move, if it's legal, figure out how many points you get for playing it and what the next position is, how many points you get from that playing out that next position to the end of the game, and that's how many points you get for that move. So this could describe sort of lots of games, given suitable implementations of these functions. Although I guess we are assuming that there are 4 legal moves in every position. So this is some rules of the game. And then also that you move to this clear state if none of the moves are legal. Okay, so that's actually the entire DP function. So this is enough to tell us for any game state how many points can we score from here. Okay, so we can finally go back to main. Right, so this is the DP table that we're allocating, which is that size that we were looking at earlier. Right, so this size, I've just written them all out. That's 5 billion, 35 million, such. We're starting them all out as -1 to mark that we haven't computed it yet. So the first thing we can do is ask, okay, what is the score you get if you play out the initial state perfectly? And that tells you how many points you can get in the game. But we actually want to know more than that, right? We want to know not just how many points you can get, but actually how to get those points. Right? Because if you tell me the best score I could get in this game is 103, I have no idea how to do that. So we can also compute that from the DP table. And this is sort of a typical kind of thing that you might want to do with DP. Right? DP is often good for figuring out sort of the optimal score or something that you could get by making a bunch of choices, because it effectively just brute forces over all of them, so you know that it is doing as well as it could. But if you actually want to know what choices to make, you have to do a little bit more work. And it sort of looks a lot like running the DP again. So the basic idea is that right, you have your starting state, and then you know how good every state is, right? How many points you can score from any state of the game. And so to find a path that gives you the maximum number of points, you should just make the moves that keep you getting the maximum number of points. Right, so we know how many points we should get from the game. And we can say, okay, well, if we play this card from pile 1, can we get that many points? And if the answer is yes, then we know that it's okay to play that card from pile 1, right? And then we can keep going. And if the answer is no, we know that, okay, well, playing that card from pile 1 is a bad idea. Hopefully some other move, we must have been able to get the maximum number of points from some other move. And so that ends up looking a lot like running the DP again. Even though, anyway, so it's doing this. So let's see how that works, right? So we have our starting state, and while we're not done with the game, check that we're still on the path to get the best score, right? Also keep track of how many points we've gotten so far. And then this is keeping track of whether we found a good move to play. So if it's a legal move, and our current points, plus the points that we would get from playing this move, plus the points that we would get if we played out the rest of the game after playing this move, is the best possible score, then we know that this is a good move, right? We can make this move and still get the best score in the game. So let's just do that. We'll make the move. So mark down that we've made a move. Add the points that we get from playing this move to our total. Print out that, this should be cout. Print out that we're actually going to make this move, right? So these are the instructions to the user, to me, that I'll follow to actually play out the game, right? So it tells us what stack to play from, what card we will be playing, how many points we should get from playing that card, and how many points we should have after making that move. And then actually like make the move, right? So move to a different state of the game. And then the other thing that could happen is that none of these moves are allowed, in which case it must be time to start a new stack. So, right, we sort of, even though that's not a choice that you get to make while playing the game, it's forced on you, right? We still represented it as a transition in a DP state, right? It's a new state of the game according to how we kept track of the states, and so we need to explicitly do that. And just as a convenience, I printed out that we're starting a new stack, just so the person executing these instructions can follow that. Right? I mean, all we technically would need to print out is just like which stacks to play. Right? We could just print out a list of 52 numbers from 1 to 4, which is which stacks to play. But it would be harder to keep track of sort of where you were. So this is putting out extra information for you. That should also be cout. And that's actually the entire program. Right? So figure out the best score, and then compute the path through the game that gives you that best score. And you can see that that is what we end up outputting, right? The best score, and then what moves to make that, slowly over time get you to that score. So that is it. Yeah, I thought this was pretty neat. Because, this wasn't like designed to be a programming problem, right? This is actually designed to be part of a video game. But it turns out that, the way they set up the rules, if you're clever, you can figure out how to give a DP solution that can play this game perfectly. So, I think it's neat to find sort of real-life applications, if you consider video games real-life, real-life applications of these, programming techniques. So yeah, that's it. Hopefully you thought that was cool. This is how to solve Cribbage Solitaire from Mobius Front using dynamic programming. So that's it.